Hey everyone, welcome back. Today is day 5 of my 30-day FAANG grind, and I'm solving 6 to 10 LeetCode problems daily, breaking each down on video and sharing with all of you on YouTube. I'm Divya, by the way. I've interned at Massachusetts Institute of Technology, where my area of focus was on statistics and machine learning. Currently, I rank at top 0.3 on LeetCode at a global level, and like most of you, I'm also a very big fan of LeetCode. Over the last few days, we have tackled sliding window, two pointers, prefix and suffix based problems, and also problems based on string. Today's focus is on stacks. We'll be tackling problems based on monotonic stacks, next greater or smaller elements in the stack, and problems of such nature. These problems will teach us the structure, flow, and how to handle state across elements, which is key in interviews. Before I begin, if this video helps you, please drop a like and consider subscribing. You can also share my videos with your friend. Let's begin. The problem that we're tackling today is trapping rainwater, lead code 42. It is a hard labeled problem. This is the description of the problem, and these are the constraints. Let us go to the dashboard and we will try to investigate and find a solution for this problem. Before I begin, let me tell you that this is a really interesting problem. We have been given height as an array where each value in the height, it represents elevations on a map. Generally, you can think of it as a flat map, okay, just for the convenience. And these are the values of the elevations. And we have to return the water these elevations can trap, or in other words, the water that can be trapped between the valleys of these elevations. For example, if you look at the picture, at index 0, we have 0 elevation, which points to this. At index 1, we have an elevation of 1 in black color. At index 2, we again have an elevation of 0. Then we have an elevation of 2. Then again of elevation of 1, which is this part. Then again of elevation of 0, which is this. Then of 1, which is this. Then of 3, which is this, okay? And so on and so forth. These blue things that you're seeing, they are the water that is getting trapped. Cool. So one of the point where the water is getting trapped is at this point. Then then lots of waters are getting trapped at this point and at this point. In our question, it is also given that the base or the width of every elevation will be 1, whether that is an elevation of height 0 or of any arbitrary height. Okay, the width, which is this part, it will be of length 1 unit. Now we have to return the amount of water that can be trapped in like the units of that water. Okay, for example, if you make a count over here, we have 1 unit of water that is trapped over here, 1 unit there, 2 units here, 1 unit there, and 1 unit over here. So how many is it? 1, 2, 3, 4, 5, and 6, correct? So in this diagram, so for this case, the unit of water that will be trapped is of 6 units. Okay, let us move forward and let us try to dig in a deep little more. Okay, let us ask ourselves a question. How and when will the water be trapped? And what does it even mean by water to get trapped? I have 5 cases over here. And as we proceed with each of these cases, by the end of 5 cases, we will be able to understand what it exactly means for the water to be trapped and when not, the water will not be trapped or whether it will be trapped or not. Okay. For the first case, our elevation is of height 0. There is no elevation on this map. Every water that comes or is poured on this map, they will just spill over. No water will be trapped. In the second case, we see that we have an elevation of 2, which is this one, followed by an elevation of 0, followed by an elevation 2. So if the water rains, the water will be trapped between these two elevations. How many units of water will be trapped in this region? Unit of water 1, unit of water 1, which sums up to unit of water 2, correct? How many units of water will be trapped on this part? If the water falls on this, what will happen to the water? Think logically. If the water will fall on this, will the water be trapped? Probably no. Why? Because the water will spill down, correct? Either on the left or on the right. Similarly, on this case, on the left or on the right. But in this case, the water cannot spill, right? Because there is an elevation boundary on the left, similarly an elevation boundary on the right. So every water that falls in this region, they'll be trapped, correct? By the boundary on the left and the boundary on the right. What if we just have a boundary on either of the side, not on both the sides, but either of the sides? Either we have boundary on the left or we have boundary on the right. That thing is tackled by case 3. Let us take a look. We have an elevation of 0, followed by an elevation of 2, followed by again an elevation of 0. If I am at this point, do I have any boundary on the right? Yeah, I do. Do I have any boundary on the left? No, we don't. What will happen if the water is poured over this region? Let us see. If the water is poured on this region, most probably the water will spill from the left because there is no boundary on the left for the water to trap, right? Similarly, in this case, we have a boundary on the left, but we don't have any boundary on the right. So in that case, any water that is poured on this region, it will spill over to the right. Okay, cool. Now let us look at the case 4. It is an interesting one. We see when we were looking at case 2, we saw that on the left and on the right, we had an elevation of equal heights. Cool. But what will happen if we don't have an elevation of equal heights, as in case 4 or as in case 5? Let us take a look. We have an elevation of height 1, followed by 0, followed by an elevation of height 3. What will happen in this case? The water is poured on this region. 1 unit of water will be trapped here. What if water gets on getting poured over here? Then, like, what will happen after that? If the water is perpetually falling in this region, even after it reaches the height of the left boundary, it will start to spill over to the left. Why is that the case? It is the case because from this point, the maximum height on the left was this part, correct? And from this point, the maximum height on the right was this part, right? Among those two maximum height, which height was acting as an upper bound for the water to rise? The height on the left part. Why? Because between the maximum height on the left and the maximum height on the right, the minimum height of those two maximums was the one which was responsible or which was acting as an upper bound for the water level to rise. Okay. Maximum on the left, maximum on the right, and minimum of these two is responsible. As you can see, the minimum is this one, right? So this one is responsible or it is acting as an upper bound for the water level to rise. So what will happen? Just to reiterate once again, water will fall down. It will rise, 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 rise. It will reach this height. Afterwards, it will start to spill over. So what did we conclude from this point? We conclude that minimum of the maximum on the left or the maximum on the right. Minimum of these two heights, either on the left or on the right, is responsible for or it is acting as an upper bound for the water level. Okay. Similarly, in this case, which will act as an upper bound for the water level? Minimum of the left and of the right. This is the left maximum, this is the right maximum, standing at this state, standing at this state. Okay. So the minimum of this and this, which is that? It is this, right? The one on the right. So this will act as an upper bound for the water level to rise. So the water level will keep on rising, 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 and then it will start to spill over. Okay. On the right. So I hope you understood one thing. One thing that we can take away from here is that for the water to be trapped, there must exist elevation. Elevation on both sides. Okay. There exists an elevation on both the sides for the water to be trapped. Okay. Let us look at this example. Suppose I am at any of this state in the between. Okay. What will happen if the water is poured down? First of all, the water will attain a level of this one, then of this one, then of this one. What after that? So that if the water attains the level of this one and if it keeps on pouring, the water will start to spill over to the left. Why? Because at any point in between this range, the maximum on the left is this one, the maximum on the right is this one. But which one is the minimum among these two things? The max right or the max left? The max left is the minimum. So as we deduced above here, the minimum of the left max or the minimum of the right max will be responsible for acting as an upper bound of the water level. And after that, the water level will start to spill over from either of those boundaries where the minimum of the maximum is. In this case, it will start to spill over from the left. Okay, cool. All right. That was a little mouthful and exhaustive discussions above, but I think it was important to give you an intuition of what is going on. Now, let us look at this equation. Before I proceed any further, let me tell you directly. This equation is extremely essential and is the heart of our solution. Okay, we saw above the first part of this equation, why it was important. Cool. But hey, why are we subtracting current height out of that part? How does it make sense? Let me walk you through that. Suppose I'm at this part, elevation is 0. We have a left height of 2 and a right height of 2 from this state, correct? The max on the left and the max on the right. What will be the level of the water that will be trapped? How will it depend? How will it depend? It will depend on the max height on the left or the max height on the right and the minimum of both of those two. In this case, since they are equal, so it will depend on either of those, the right or on the left. So the water level in this case will rise up to this part. And how many units of water will you trap? The units of water that will you trap is 2. How? You see the first unit of water, this is the second unit of water, and it sums up to 2, correct? Notice that here we had an elevation of 0. Cool. Now let us look at this example. It is almost identical to the first one, except the case that instead of having an elevation of 0, now we have some sort of elevation. So structurally, our map looks like this. What will happen if the water is spilled over this region? What will happen if the water is poured on this region? How many units of water will we be able to capture? Let us see. Water is getting filled and it will stop at this point. Why? Because of this elevation. So how many units of water are we able to capture? Total units of water in this case is just one that is getting captured, right? Why one? Because the remaining one was subdued or replaced by this elevation, which also had a height of 1, right? So if the total amount of water in this case, if that was to be captured was 2, but it was replaced by an elevation, this is the elevation height, right? So the amount of water that is getting captured is just 1, right? So I hope it made sense to you why we are subtracting current height. Current height, subtracting current height, it is, you can think of, it is like, making sure that we do not come to a wrong calculation and we always stick to the right calculation. And if we do have an elevation, in that case, if the water was supposed to be trapped till this region, but 1 unit of water is getting pushed up because of this elevation, and that unit of water is either spilled on the left or on the right. So we are just left with a single unit of water, okay? So that was all there was to this specific equation, why it is important for us. Now let us move to an example. We'll do a dry run of an example and we'll see how it goes, okay? Suppose we have an elevation of this type, 4305. This is the diagram, 4305. We have to compute the maximum water that can be trapped. First of all, let us just look at diagrammatically how many waters can we trap in this region. So this will trap 0 unit of water, 1 unit of water, right? Will there be any unit of water that will trap on top of this part? No, right? Because there is no boundary on the left of this part, right? So water will spill over. Look at this case over. Case number 3, right? We talked about that. In this case, the water that will be trapped will be 1 because of elevation on the left and of elevation on the right, which is the maximum here and the maximum on the left, and minimum is the left one, correct? What if we are here? How many units of water will it trap? 4 units of water will be trapped, correct? Why so? Because of the left elevation max, right elevation max, and minimum of these two is the left elevation max, whose height is this part. So the amount of water that will be trapped will be stuck at that region, and it will go on and go on and go on, and it will fill it up till that part, right? So there are 5 units of water that are getting trapped. 1 unit here and 4 units there. 1, 2, 3, and 4, correct? So total 5 units of water. All right. How did we know that we had 5 units of water and how to compute that? In order to make a computation, what we do, if I am standing at any index in the map, I will compute the left maximum from that index and the right maximum from that index. Then I will take the minimum of the left max at that index, right max at that index, and then I will subtract current height from that. And when I perform this equation, it will give me exactly how many units of water can be trapped at that specific index. Okay. Let me walk you through it. We have two arrays, the left max array, the right max array. As the name suggests, it does exactly what it states. For any given index, left max stores the left max for that index. For any given index, right max stores the right maximum from that index. For example, if I'm at index 3, what is the left maximum? The left maximum is 4, which is true. What is the right maximum if I'm at 3? It should be 5. Let us see. And it is 5. How will our computation work? We will take the minimum of the left max, which is 4, right max, which is 5, subtract current height, which is 3, and it will give me 1. So at this index, the amount of water that we are trapping is just 1. Let us verify that pictorially. We are at this index, index 3. From this index, the left max is what? 4. The right max is what? 5, this one. And the minimum of this we have to take and subtract the current height, which is 3, and it will give me 1, which is the water that is getting trapped here at the top, correct? Similarly, if we just perform this operation for every single index, we will come up with an array, something like this. At index 0, we have the amount of water that will be trapped is 0. And at the last index also, the amount of water that will be trapped will be 0. Just to be clear, once again, I think I did not mention this point, but it should have been obvious. At the edges, at the extreme edge on the left and at the extreme edge on the right, we cannot trap any water because on either of those edges, the water will spill over. For example, if I'm at the left edge, there is no left boundary, so the water will spill to the right, left. If I am on the right edge, there is no edge on the right, so water will spill to the right. So in that case, always it will be the case that at the edge, amount of water that is getting trapped is 0. Water can only be stored after the edges, okay? In any region in between them, okay? So this is the simple calculations of the array, and if you sum it up, we get 5 units, which is exactly what we saw in the diagram, right? Cool. Now this is the code. What do we do? I first declare the left maximum, and this is how it is getting computed. It's pretty simple. For any index I am at the array, I'm in the left array, left max array, I will compute the maximum at that index by taking I minus 1 on the left and height minus 1, and then compare the max and then store in li. Similarly, for right index, right max, I will start from the end, which is what I'm doing here. It is much more of a Python code. I'm iterating from the back, and for any index, I will look at the elevation on the right by I plus 1, and then also the height on the right by I plus 1. And once we compare between those two things, we store it in Ri, okay? And once my left max and right max is computed, I will just iterate over once final time. But before I do that, I will have a value answer equals to 0. And I will run across a loop to the entire array. And then I will compute the units. How? Using the same equation above, which should have been pretty obvious now. Minimum of left maximum, right maximum at the index k, because I'm iterating at k index iterative. I'm subtracting the height, current height at value k index k. Okay? If my units is greater than 0, it would mean that we can trap water. So we will sum it up. Oh, by the way, every time we do these calculations, there might be a possibility that our value will be either greater than 0, less than 0, or equivalent to 0. If our value is either equivalent to 0 or less than 0, in that case, we will assume that the total amount of water that is getting trapped is 0 unit. If it is less than 0, you can think that our water is getting spilled, okay? And we cannot trap. So for negative or 0, the amount of water stored in units term will be 0. The water will only be captured if the units is positive. And this units is getting completed over here. Okay, cool. All right, so the time complexity for this thing is order of n. Why? It should be obvious because we are just iterating to the loop over here, and over there. Okay, actually it should be times 3, but again, that do not make any sense. Space complexity will be of order of n. Why? Because of the arrays that we declared, 2 arrays, left max array and right max array. Cool. So this was of method 1 of the solution. Method 2 of the solution works exactly like this, apart from the fact that in that case, we will optimize the space from order of n to order of constant. Let me scroll down, and this is how method 2 will work. In method 2, we will have 2 different pointers pointing at both of those ends, namely left pointer and right pointer, left pointer and right pointer, left at 0, right at the right end. Okay. We will also have 2 different variables, left max and right max. What does they do? At any state of our index or at any position of our index, left max will store the left max from that index or from that state, and right max will store the right maximum for that state, current location of index I am at. Okay. For example, if I'm at this position, so in that case, the left max will be 4 and right max will be 5. Okay, cool. So initially, the value of left max and right max will be initialized to the value of the left end and the value of the right end. Value of the left end is 4 for the left max, value of the right end is 5 for the right max. Okay, I will start to iterate and I will go on within the loop as long as left is less than right, left pointer is less than right pointer. We'll go on scanning the entire array. Now, here comes the really interesting part, and I want you to follow it very carefully, okay? I ask myself a question, a condition. Hey, if left max is less than right max, what does it mean? It means we have left maximum and the right maximum, and among those two, the minimum is left maximum. And once I have found the minimum to be left maximum, we'll proceed as follows. We'll increase the left pointer by 1 first, followed by making a comparison to the left max by this equation, left max and height of the left, and then we will store the units in this manner, left max minus height of left, and that will be stored in answer plus equals to whatever that value is, correct? I hope this makes sense. This is pretty identical to these equations that we had solved above. If this is the left max minus the current height, okay? This height is the current height, and left max is the minimum of the left max and right max. Why am I telling that it is the minimum? Because of this equation, right? It says that if left max is less than right max, which it means left max is smaller or minimum, then we proceed with these orders of equations, okay? And similarly, if right max is minimum, in that case, I move right pointer 1 to the left and we proceed as follows, okay? I just want to dig little deep now, just for out of curiosity, as in why it is happening, like what are these things and how to get an intuitive sense of what is happening over here. Assume I have an example. Suppose my left max right now is this one and right max is this one, okay? And the current index that I'm standing at is this of an elevation 0, okay? What would happen in this case? In this case, it should be pretty obvious. Amount of water that will be stored will be at this point will be 1, correct? Looking at this equation. Left max is what? Left max is 1. Height is what? 0, right? So it will be 1, correct? For this case. Left max is 1, height is 0. So the amount of water that will be stored will be 1 unit, okay? But what will happen if instead of an elevation of 0, what if I do have some sort of elevation like this one? What will happen then? And this elevation, as you can see, it is greater than the elevation on the right. That will affect how second line of code works. Now, let us look at this first case. In the first case, left max was 1 and the current height that I'm at is 0. So in this case, the maximum will be 1, comma 0. And if I'm at this index, so in that case, the maximum will remain to be 1, okay? But if I come to this index, so what is elevation 1, 2, 3, 4, 5, right? Let us look at this code once again. Okay, maximum of left elevation is 1, current elevation is 5. So what is the maximum of Lmax right now? Lmax right now it becomes 5. Remember this. Right now, at this standing at this point, right now standing at this point, my Lmax is 5. Let us come to this next code. Okay, it says Lmax, which is 5, minus height, which is 5. Amount of water that should be stored at that index is at this point is 0, right? Is that the case? Let us look at pictorial. I'm here, water comes over there, right? It starts to pour down over here. Is any amount of water getting stored on this point? The answer is no. Why? Because there is no left boundary to capture it on the left, no right boundary to capture on the right. So the water will either spill from the left or from the right, which makes sense because there should be no water at this point, which is exactly what our equation is stating, which is exactly coming from this part. And Lmax is coming from here, and it is getting computed at this part, right? So I think you understood what I'm trying to say. Okay, I just wanted to draw this to a diagram just to tell you the importance and give you a visual intuition of these two codes and how they are working. Similarly, you can interpret them for these two codes as well. So yeah, that was all there was to this problem. The time complexity is bounded within linear. The space complexity is a constant one because we are just declaring a few variables of order of one type: left max, right max, left and right. Okay, cool. So I think this was one of the longest videos I made on the LeetCode. I hope you understood everything that I was trying to explain, especially these cases that I went through, these cases and these diagrams, where this equation is coming from, the importance of this thing, why am I subtracting current height from that? These two examples where the current elevation is 0, followed by a current elevation of 1, and how that is getting interpreted over there. Then these examples that we went through, these diagrams, how the summation is getting done, how this is computed. But more importantly, we also spent time understanding these three lines of code, especially these two lines of code, using these two diagrams above there, right? And how the computation is getting done. Again, I just wanted to give you a very, very in-depth, crystal clear explanation of what is happening in this code, why it is happening, and how it is happening. Okay, cool. Let us move to the LeetCode dashboard and we will try to submit the solution. Since we had two methods, the first method is required order of n space. So, oh, why is it not working? Oops, come on. Okay, I'm not sure what's wrong. Okay, it's set. All right. So, this is the code for order of n space. You can see at line number 7 and at line number 4, we are declaring left max array and right max array, and the computation is getting done. I'll just run this code and you'll see that the test cases has been accepted as it should be. And for the second solution, it is this case where we are just using pointers, as you can see on line number 5, 6, and 7. And yeah, and it requires order of add time with order of one space. If I run this down, you can see that it will also be submitted and the test case passes, okay, as it is the case. All right, cool. So yeah, that was all there was to this problem. I hope you understood everything that I was trying to explain. But still, if you might have doubt, please, please ask me in the comment section. I'll be much more happy to help you there, okay? Until then, see you in the next video.